Okie dokie. 5.6 is all about how we're going to divide our polynomials. There's very few actual steps to be written out for these. I will give you a minor gist of what's going to happen, and then we're going to do a bunch of examples so that you can see. These are not exhaustive examples. There's other ones that you can see, but I did try to pull ones off of the homework so that you would know what is going to be coming your way. And there's always time at the end that I can do more examples. I actually added an additional example that's not in my handwritten notes, so I will let you know when that one comes up. The first way we can divide polynomials is by a monomial. Remember, monomial means one term. So if we are dividing by a monomial, the easiest way to approach it is to divide every term of our polynomial by that monomial, is what's going to happen. So what I mean by that, and we'll take a short polynomial like 9x plus 54, and we will divide that all by 9. So we're taking a binomial, something that has two terms, and dividing it by a single term, a number, just the 9. So when we are doing this, you can think of it as splitting, because there's only one term on bottom. We can split the top into two separate fractions, where we have 9x over 9, and then plus the 54 over 9. We can split it up. If this had 3 terms or 5 terms or 10 terms on top, you could do that, because the bottom only is a monomial. If this was reversed, I couldn't still do this. I can't do this if I have a binomial or a trinomial or a polynomial on bottom. I can't do this split. I can only split it up like this because I have a monomial on bottom. Okay? So here I see with 9x over 9, notice I have a 9 on both top and bottom. So that simplifies away, leaving me with just the x. And then what is 54 divided by 9? 6. It actually simplified down to a nice number. Sometimes those will. Sometimes they will just be able to give you a simplified fraction where certain things will cancel out, but you're still left with a fraction as your answer. Fractions are not a problem as long as they're simplified. But here we did just get to an x plus 6, a pretty nice answer in the grand scheme of things. So the splitting method only works when we divide by a monomial. Otherwise, you're doing magic math. Now, a monomial can be just a single number, or a monomial can also have a variable with it. This is still considered a monomial on the bottom, the 7x, because these two things are being multiplied together. There's no plus or minus in between them, so it's still a monomial. So we can approach it the same way we just approached this last one, where we split and we simplify. We'd have the 28x squared on top over the 7x minus the 14x over 7x. We can split it the same way. And we simplify it the same way. Except here I see, okay, I have 28 over 7. That's not going to completely cancel like my 9 over 9 did. But 28 is what times what? 7 times 4, yeah. So 7 times 4, so there is a 7 on top, so I can cancel. And then remember that x squared is the same thing as x times x, so there would be an x that cancels. That would leave me with a 4x for this first term, because everything else canceled away. Same thing over here. Automatically, I see that I have 1x on top and 1x on bottom. Those can cancel. 14 over 7, well, 14 is 7 times 2, so again, my 7's canceled, leaving me with just this 2. Don't forget, though, that there's a minus in here so that you just write it down correctly and don't put a plus 2. if you like factoring, which is something we haven't discussed in this class yet, but hopefully you've seen it somewhere else in your life, and you enjoy the process of factoring or pulling out things that your terms have in common, these problems can also be approached from a factoring perspective. I don't generally teach it that way, but it does work a lot of times with that. And what I mean by that is I'm going to use this problem we just did as an example. This is just another method. I'll call it the factor method. The factor method doesn't always work as nicely because it just depends on what we're dealing with. But this one is a quote-unquote nice problem. So the factor method, the way that we would approach it, is we'd look at the top where we have our polynomial, and we'd say, okay, between the two terms that are on the top, what do they have in common? Is there anything I can pull out of it? This is factoring. We will be doing this later in the semester as well, but if you already are prone and like factoring, I just wanted to present this as an alternative. Well, if I look at 28 and 14, I may say, well, I know those both have a factor of 7, so I can pull those out. Factoring is like the reverse of distribution. So both of these would have a 7, and then I look at the term here, I have an x squared and an x, so they would both have an x. So I could pull that out. So what does that leave me then if I take that out? Well, 7x times what would give me the 28x squared? Well, 7 times 4 gives me 28. 7 times, or the x times something would have to give me x squared, and it would be the x. Then I go over to my 14x and say, okay, well, I don't need an x term, I just need a number. 7 times what gives me 14, and it would be 2. If you do the factor method, you'll notice that we pulled out exactly what we had on bottom out front, which completely cancels, leaving us with this 4x minus 2, which is exactly what we got up here. You're going to get the same answer. It's just a different method for doing it. When we get to our big factor section, or big factor chapter later, this is what we will be doing. But like I said, some of you may be very comfortable with factoring, and I wanted you to know you can use that method. You can use the canceling method. I'm not going to make you pick one or the other as long as you are doing one that's mathematically sound. Are there questions before we do something different? Yes?
I'm not super great at factoring, but...
Okay, then don't do this method yet.
Okay.
You just do the cancel method, and as we progress through the semester, you'll gain more tools that'll make the factoring method easier.
Okay.
Okay?
Yeah.
All right. So, dividing by a monomial, you split them, you simplify them. The other one we're going to look at, the other big branch, is dividing a polynomial by a binomial. Or really, this can be stated as dividing a polynomial by a polynomial. We're going to keep it, I think, almost always to a binomial, but it works no matter how many terms you have in it. And this is long division. Long division is the original way you learned division way back in grade school, like with regular numbers. And we're actually going to do a numerical example first because it's a great way to remember how this works. So I'm going to do just a regular old number example to refresh your memories on how long division works. We are going to take 29 divided by 2. And we're going to do it the old school long division way. We can't use a calculator. We're going to figure it out the long school way. So here's how we would do this if we were doing long division. This second number is what would be put outside of our division bar. We had a division bar like this, and we'd put the 2 out here. We'd put the 29 under here. It's just ringing some bells way back in the distance. It's probably been a hot minute since we've done division like this because we all get really comfortable with our calculators. But we can't use our calculators to do long division with polynomials, and so that's why it's good to have this process. So the way long division worked is we would look at our number outside, and we'd look at the number in here, and we'd go term by term with our number. And we'd say, okay, can 2 go into 2? Like, is the 2 underneath divisible by the 2 out here? And the answer is yeah, 2 can go into 2. How many times? 1. I can take 1 times 2, and that gives me 2. I can't take 2 times 2 because that would give me 4, which is too big. But I can take 1 times 2, and then here's how it works. We draw the line, change the sign. That's a really big minus sign, sorry. Change the sign. Draw the line, change the sign. So that we do subtraction down. 2 minus 2 is 0. And we bring down our next term, which is 9. And then we do the process again. How many times can 2 go into 9? 4, right? If we go 5, that takes us up too many. But 4 times 2 is 8. And so that keeps us under 9. So we draw our line, change our sign, and we would be left with 1. Now 2 can't go into 1. So this down here is our remainder. Because 2 doesn't go into 29 perfectly. We have a remainder. We have something left over. And so what do we do with this remainder is we stick it over what we were dividing by. So up here next to the 14, I'm going to write 1 over 2. You stick your remainder on top of what you were dividing by, and that gives you the fractional part to go with your whole number. So 29 divided by 2 is 14 and a half. But if this remainder had been 2 or 3 over like 4 or 5 different numbers, we could still write a fractional equivalent over here just like that. It always works. And that's how you're going to be expected to give your answers today with your polynomials, is by putting your remainder, if you have one, on top of what you were dividing by. All right, we ready to see it with polynomials? Same process. Same things we're asking. We are going to take x squared plus 6x plus 8 divided by x plus 2. So here we have a trinomial, 3 pieces, and we're going to divide it by something that has 2 pieces, a binomial. What you're dividing by always goes outside of your division bar. So we'll have the x plus 2 outside. We'll have the x squared plus 6x plus 8 inside. But we're going to approach this just like we did with the numbers. Exact same thing. Here I had 2 and I was like, okay, how many times does it go into 2? I didn't ask how many times it went into 29. I just went 2 into 2. So over here, I'm going to look at the first term of my binomial, the number out here, which is the x. And I'm going to say, okay, how many times can x go into x squared? Or the other way to ask it is, what can I multiply x by to give me x squared? An x. If I take x times x, I'll get x squared. So I'm going to write an x on top. And then I say, okay, x times x gives me x squared. But I can't be done and just write that and then do my subtraction. There's also this plus 2. So I say, okay, x times plus 2 would give me a plus 2x. So whatever you find to put on top, you have to multiply it by both of your terms out here with your binomial. Then you draw your line, and you're going to change your signs. So it was a plus x2 or a plus x squared, so that becomes a minus, and it was a plus 2x, so this becomes a minus as well. Try to make that as bold as I can there. So our x squareds go away, and then our next term we have 6x minus 2x, giving me a 4x, and then I bring down the plus 8. You keep bringing down your terms until you run out of terms, is what ends up happening. We brought down our 9 with our number, and then there was nothing else to bring down. We bring down our 8, and then we're going to do it again. I'm looking at x to 4x. What do I multiply x by to get to 4x? Four. So on top, I'm going to put plus 4. I'm taking 4 times x, which will give me 4x. Then I'm taking 4 times the plus 2, which will give me a plus 8. Hopefully you can see what's going to happen, because I'm going to draw my line, which means I change my signs. So I have 4x minus 4x, that gives me 0. I have a positive 8 minus 8, which also gives me 0. I usually put a smiley in there because I'm silly, and this tells me, but I'm happy because this means there's no remainder. If you get a 0 down here at the very end and there's nothing left to pull down, that means there's no remainder. So this was perfectly divisible, and the x plus 4 is the answer. We're going to do another one. We're going to do a couple of them. Again, there is a way to do this with factoring. We will do that at another time, though. Like later in the semester. All right. Let me get a new sheet of paper. All right. Example B. Let me see where this is at. Okay. For you. Will be 6x squared minus 5x plus 5 divided by 2x plus 3. And we will be using long division because this has 2 terms in the bottom. So I'm going to put the 2x plus 3 outside. And I'll put the 6x squared minus 5x plus 5 inside. And I look and I say, okay, I have a 2x on the outside and a 6x squared on the inside. What can I multiply 2x by to get me a 6x squared? So what do I multiply 2 by to get to 6? 3. And then what do I multiply x by to get to x squared? Yeah, an x. So I'm going to multiply by a 3x. 3x times 2x will give me a 6x squared. Because we're always trying to eliminate the terms as we move across, because hopefully we have no remainder like on the last problem. Bless you. Then I have 3x times the positive 3. 3 times 3 is 9. And then I have the x. I'm going to draw my line, change my signs. My 6x squareds go away. And then I have a minus 5x minus 9x, giving me a minus 14x. And I bring down the plus 5.
Hold on, where you get the 9x from?
I took 3x times this plus 3 that's out here, because we have to take whatever we put on top times however many of the terms over here that we actually have. And then when I changed my signs, it became the negative. Now I'm looking at the 2x, and I have a minus 14x. So what do I multiply 2x to give me a minus 14x? 7, but this is a positive 2 and this is a negative 14, so it's going to be a negative 7. So negative 7 times the positive 2x will give me the minus 14x. Then I take negative 7 times the positive 3, which will give me a negative 21. Draw my line, and I change my signs. They were negative, so now they become positive. Before they were positive and they went negative. Negative 14x plus 14x, that goes away. But over here we have a 5 plus a 21, giving me a 26. and there's nothing else left for me to pull down, this is my remainder. And that's okay. Remainders can be single numbers, whole numbers. They can even have variables with them. But here I have 3x minus 7, and I need to stick my remainder over what I divided by. So my remainder is positive, so I'll put a plus. Then I'm going to put 26 over 2x plus 3. This is exactly what we did when we had our numbers, and we did 14 and a half. The half came from the remainder that we had, sticking it over what we were dividing by. Here I stuck my remainder over what I was dividing by. This is how Pearson will expect you to put your answers in. I know because I went on there and I played around in it to make sure. We're going to keep going. We're going to keep doing some examples. Make sure all this is clicking. Yes.
Okay. And like the 1/2, it's just kind of putting up there that, because the way it looks like here is like there's no like terms here.
Correct.
Okay. Because I'm like, is usually I wasn't, thinking the plus sign. I'm like, well, that way, the plus the -7 would be above the numerator, would be in the numerator instead of
So the -7 is almost like our, where did it go? It's like the 4.
Okay.
So we wouldn't stick our remainder underneath or over the 4 because it has nothing to do with that. That actually was one of the factors. And so we put the plus here because it was a positive 26, and we added on. Some people...
Because, normally with me with the remainder, I wouldn't add, unless it's negative, I wouldn't add a sign because it's
right.
you're supposed to add it.
Right. And with a number, we don't really have other terms. It's all a single term, which is why we don't have that plus or minus in there. You will see some people write this as 14 plus 1/2 like this. We would just not consider that simplified, and that's why we would write it as the mixed number over the 14 plus 1/2. But you do see people every once in a while, and that's how they would teach their students. I like to teach to finality, which means I like to teach until we are completely simplified, because that's the best way. And so we don't have pluses or minuses when it comes to just numbers because it's a single term. But here we have multiple terms at play, and so we use the pluses and minuses to separate those different terms. So really what you're always going to see, regardless of if you have a remainder or not, notice what happens on top of our division. We had an x squared term that we're dividing by an x term, and we get an x term. That's because x times x gives me x squared. And then our next term is a constant term. There's no x involved. After your constant term on top, the only thing left is a remainder. That's it. You can't have another term that has an x in it. So that's something to always kind of be aware of. Here, with our one that did have a 0 remainder, I found an x and I found a 4. The next thing could only be the remainder if there was one, but there wasn't in this case. We're going to do a couple more examples. On the actual scanned-in page, there's 2 additional examples, but I found one off of the homework this morning that I really want to do because there's an extra step that you have to take every once in a while, and I wanted to make sure that you were aware of it. And then we'll go back and do the other examples. So I'm going to call this example C because I want it to actually be part of your notes. Straight off of one of your homework assignments in Pearson. Now yours may show different numbers, so I can't tell you which number it is because it may be 7 and 12 instead of 9 and 19. But this one has an important principle at play with the polynomial that's on top, and we have to talk about it. Do you notice anything about your x's when you look at the 9x cubed versus the negative 19x. Thinking about like the polynomial we just did up here. We had a 6x squared, a negative 5x, and a positive 5. Here we have 9x to the third minus 19x. It's missing the x squared term. We don't have one in this one, do we? And that's okay. We don't have to have one. But when we do division, we have to have a representative for every single term. And so if we skip one of our variable terms, we still have to put in a 0 placeholder, is what we call it. And here's the number thing that kind of goes with it. If I write out the number, this, what number is that? This one. What number is this? 11. But what if I was actually meaning it's 101, but I didn't write the tens place in because there's just no tens? Like, that doesn't really make sense because in numbers we use zeros as placeholders. There's no tens in this. There's 1 100, there's no tens, and there's 1 1. But we are used to looking at 0 as a placeholder with our numbers. And we have to use that 0 as a placeholder with our polynomials when we're doing division. So when I go to write this out with my long division, I'm going to have the 3x minus 1 outside like normal. But when I go underneath, I'm going to start with my 9x to the third. I don't have an x squared, so I'm going to put plus 0x squared. I'm putting in that 0 placeholder. Because 0 times x squared would give me 0. I'm not adding anything to it. I'm just writing in a representative. I'm just making sure that I don't forget that there is that spot there. Because if I leave it out, it changed my number. If I leave it out, I'm not communicating well with what I'm trying to do. Because if I'm trying to do a problem with 101, but I only write the places that have value, that doesn't help anybody. So if there's a missing variable placeholder, or missing variable, make sure you put a 0 placeholder in there. The rest of the problem works the same way. 3x to 9x to the third. So 3 times what would give me 9? 3. X times what would give me x to the third? X squared, yeah. Because this would give me x times x, this would give me an x, that's going to give me x to the third. So 3 times 3 is 9, x squared times x to the first is x to the third, and then I take 3x squared times the negative 1. That'll give me a negative 3x squared. Then you draw your line, change the signs. So that my 9x to the third minus 9x to the third goes away. I have 0x squared plus 3x squared. That'll give me a positive 3x squared. And I bring down my minus 19x, because that's my next term. That's a 2. That's a sloppy 2, though. Then I say, okay, 3x times what will give me 3x squared? 1, so yeah, just 1x. So you can either put plus 1x or I'm just going to put plus x. I don't generally put the 1 out there if I don't have anything else to attach to it because it's just kind of a signifier. Multiplying by 1 doesn't change it. So x times 3x will give me 3x squared. X times the negative 1 will give me a negative x. Draw the line, change my signs. So that I have negative 19x plus x, giving me a negative 18x. And you'll notice that there wasn't a constant term either. There wasn't a number attached at the end that didn't have a variable. If you wanted to, you could put a plus 0 there as well. as a placeholder for your constant term. Because we're still not done, even though I don't theoretically have any more terms, because I can still do this. I can still say, okay, 3x times something can give me a negative 18x. There's still a common factor here. So if you want to, you can always put that plus 0 if there isn't a constant. And you can even think about bringing it down here as a plus 0. It's fine. If that makes you more comfortable, you can totally do that. If you don't need that plus 0 to know you still have more to do, that's also fine. The reason why we know there's still something we can do because is we look here and say, okay, this is an x and this is an x, and I can still multiply 3 by something to give me negative 18. That's how I know I'm not done. So 3 times what will give me negative 18? 6. But it's got to be negative because this is a negative 18. So that'll give me a negative 18x. And negative 6 times negative 1 over here will give me a positive 6. We're going to draw our line, change our signs. Zero take away 6 will give me a negative 6. So negative 6 is our, sorry, I'm trying to adjust. Ooh, sorry, the Elmo. So negative 6 is our remainder. This negative 6, not that one. This is our remainder. So we have to stick this on top of what we're dividing by. Since it's negative, I'm going to put minus here, not plus like I did up here with the 26. 6 goes on top, and what I was dividing by, the 3x minus 1, goes on bottom. All of this is the answer. And I checked it because I even typed in that answer on my problem in Pearson to make sure. And that's exactly the format they wanted in. Bless you. You have a button in Pearson that allows you to put exponents up there. You also have a button in Pearson that allows you to do fractions like this, where you can even put polynomials in the bottom. So if you are missing a term, make sure you put a 0 in there. You can even put a 0 in there for your constant if you so choose. Questions? They take practice, especially if it's been a minute since you've done any long division. Okay. Let's do one of our extra examples. So these are in my, this one was the only problem that was not actually in my notes, in my handwritten notes, because I just added it this morning. These others they're on the very last page of the notes. They're titled Extra Examples. But I wanted to do at least one of these because, sorry, that was way crooked over there for you guys. Because obviously we have a larger polynomial. This one has 4 terms. And it starts with x to the 5th, goes to x squared. It does not have an x term or a constant term. But I don't have to be concerned about that because what's in my denominator? What am I dividing by? 2x to the 3rd. That's one term. This is a monomial. This is the very first style that we saw earlier. This is a split and simplify problem. This is not a long division problem. So I can split this up to where I have 6x to the 5th over 2x to the 3rd minus the 4x to the 4th over 2x to the 3rd plus the 12x to the 3rd over 2x to the 3rd minus 5x squared over 2x to the 3rd. I liked having this one as an extra problem, excuse me, because it doesn't simplify out as nicely as the ones that we did earlier. This one gets a little bit grosser, if you would. So here with 6x to the 5th over 2x to the 3rd, 6 divided by 2 leaves me with 3. And x to the 5th over x to the 3rd, you can think about this in terms of the canceling that we've been doing, or you can think about it using your quotient rule, where you'd have x, I'll make a little note over here, like x to the 5 minus 3, which leaves you with x squared. So either method works. I typically gravitate towards the canceling method, but you can also use the quotient method that we learned earlier in the semester. Then I go to my next fraction. 4 divided by 2 is 2. I look at my x's. I have x to the 4th on top over x to the 3rd on bottom. Where do I have more x's? On top. How many more? Just 1. Then I move over to my next one. 12 divided by 2 is 6. I have x to the 3rd on top, x to the 3rd on bottom. Those cancel out. Notice what's happened. We have an x squared term, we have an x term, we have a constant term. So based on our long division, what theoretically should come next? The remainder term, right. So this one's probably going to look a little bit different than the last ones because all of these is simplified really nice, which is what our first examples had done. This one, though, if I look at it, 5 over 2, well, 5 and 2 have nothing in common, so that's going to stay. And then if I look at my x's, I have x squared on top over x to the 3rd on bottom. Where do I have more x's, on top or on bottom? Bottom. How many more? I have 1 extra x on bottom. So this one looks different than the easier ones that we did at the beginning. But it's still the same method. When we divide by a monomial, we split it up and we simplify out what we can. And this is the final solution.